Hello. We're going to talk about our basic question first. And this question, they're asking, do heavier people burn more energy? So they studied 12 women in this study, and they're asking if their lean body mass, which is measured in kilograms, has anything to do with the calories burned in 24 hours. They're asking if there's any correlation at all. So what I did first is I went into my list, stat edit, and I put in list 1, my X values, I put the mass. And then in my list 2, I put all the rates. And then I went back to my normal screen. Then I went and did calc, linreg, just to get those data points. And then I went into second stat plot, and I went ahead and turned on the stat plot and made it a scatter plot, and then I graphed it. So I graphed it in the calculator, and then I graphed it on this one right here. So as you can see on my X value, I put the metabolic rate, calories per 24 hours that are burned, and then I went by 100 each time. And then on this one, I just started at 33 and I went up by ones, and that's the lean body mass in kilograms. It kind of looks like this, but it's kind of stretched out a little bit more, so you get a little bit more of an idea of how this looks. So then it asks you to describe the direction, form, and strength of the relationship. Well, I said that it was very strong and positive correlation, and that it was linear. There it is. So I said that it was strong despite that one point that stands out, which you can see very well in this that I plotted. You can see that there's that one point that kind of stands out a little bit, but other than that, it's very, very strong. It is positive because the whole scatter plot is going up from the left to the right. See, every point is gradually going up. Even this one's gradually going up from what it was before. And then it was linear because there is a line. As you're looking at this graph, you can kind of see that there is a line that you could draw, just like right here if you wanted to eye it, and that is perfect for a line. Okay, so for our advanced question, it gives us some data on the 6-minute walk test in children and adolescents. So it's a bunch of boys that completed a test measuring the distance that the subject could walk on a flat hard surface in 6 minutes, and the distance is measured in meters. So it gives us the midpoint of the age group. So this one was like 3 to 5, and the midpoint was 4, 6 to 8, 7, etc. And then it gives us the median 6-minute walk distance in meters that they all traveled. So I just went ahead and plotted this in my X, and this in my Y, or L1 and L2, in my calculator here. And then the first thing it asks you to do is determine the least squares regression line. So I just went straight to this, my stat calc, my stat calc, winreg, enter. There it is. So A obviously is 14.7633. We want to round to the nearest 4 numbers after the decimal for the most accurate data. And then my B is 492.7977. Alright, and I just went ahead and plotted this data because it just helps me visualize how positively linear this correlation is. Just for you. So if you need the process all laid out for you, this is exactly what I did. And then it asks us to basically break down the slope for them. What is the slope? And the slope is the rise over the run, which would be the change in age over the distance walked. So for every 1 change in age, there's a 14.7633 increase in the distance walked in meters in the 6 minutes. In question 2 here, it asks us to plot the residuals and compute them. So first thing I did was go back to my list And I just went over all the way to a blank list and put in resid using my alpha and my letters down here, and I just hit enter and I got this. And then I decided that I wanted to plot that because I have no idea what it means without my plot. So turn that on. Make sure this one's off so you don't get confused looking at two different datas. Hit zoom 9, and there you go. And this is how my plot looks. I did it by 5s on the sides and 5s in the middle. And this is obviously the first point of 4 and -7 something. Then this is 7 and -12 looks like, etc., etc. And you can always go back to your list and make sure that, see, -7, -12, then it jumps up to 26, down to 8, and down to -16. Lastly, it asks us if there are any unusual features. And what does it mean if there are no unusual features? Well, I said that there were no unusual features, and the plot is approximately normal. Because despite the super high one right here, it's basically even on both sides. It's very normal. There's no unusual outliers or anything. It goes back to the regular plot that we had and how positively linear correlated that was. You kind of could assume that there wasn't really any unusual things going on. So I just went ahead and said that there were no unusual features. Our last question of the day is our AP question, and this has to do with commercial airlines that need to know the operating cost per hour of flight for each plane in their fleet. And they found a correlation between the operating cost per hour and the number of passenger seats. So they went ahead and made a graph, and our passenger seats are found down here, and our operating cost per hour is found over here. Alright, on the X and Y axis there. And so it ranged with as few as 216 passenger seats right here to as many as 410 passenger seats right here. And then the range went all the way from $3,600 to $7,800. That was the cost per hour. So it's a very big range of data. The spread is very wide, but you can see that that strong positive correlation is right there in the middle. There's a little bit of higher ones over here and lower ones over here, and we have a really big clump right there in the middle, but it's overall very strong and very positive. So our first question is basically finding the least square regression line and define any variables used in the equation. And it's asking with the relationship between operating cost per hour and number of passenger seats. So I just went right here under seats and found this 14.673, and I put that right there. And X is my variable for the number of passenger seats that you will input in that. And this 11,136 is the constant. And Y is what you would get, and that's the operating cost per hour for that certain plane, depending on the number of passenger seats you find. Our second question is, what's the value of the correlation coefficient for operating cost per hour and number of passenger seats on the plane? Interpret the correlation. So I just went ahead and went straight to this R squared percentage right here, which is 57%, and I made it into a decimal. And I made this equation, R equals positive squared, and that percentage, which I turned into a decimal, equals 0.755. And I said that it was a strong positive correlation based on this correlation coefficient, which is really close to 1, which is super strong. So this isn't quite as strong, but it's still pretty strong. And our last question of the day is, suppose that you would want to describe the relationship between operating cost per hour and the number of passenger seats in the plane for planes only in the range of 250 to 350 seats. Does this line shown in the scatter plot still provide the best description of the relationship for data in this range? Why or why not? So, super intense question here. I said no, it doesn't. The least square regression line is influenced by the 3 points in the upper right and the 2 in the lower left, like I was talking about earlier, how those are very way out here and this one's very low, and we have this huge clump in the middle. And the number of seats in the 250 to 350 range, which would be like maybe here to here, yeah. The number of seats in that range would have a negative correlation. So basically, if you took this data, only this middle data, you would get a negative correlation because from 250 to 350, it's slowly going down. And so this right here and this right here is the only thing that makes this line a positive, strong correlation. So if you took all that away, it would be negative. So that's why this last answer is no.